a point will lie on the best fit line, so the deviations become zero. So therefore, we can consider we can consider such best fit line uh, which will give us the minimum residual sum of square error. Now here we will try to understand the linear regression model by this example, where we can see that here we have a number of bedrooms in the data set, and their corresponding actual selling price. Now for 2 bedroom, we can have this actual selling price. For 3 bedroom, we can have this actual selling price. And having this data set, this is the two-dimensional data set. Okay, having this data set, we can predict the selling price. Now the predicted selling price has also been determined. Okay, now we are having the actual selling price, we are having predicted selling price. Now we can get the residuals. So we get the deviation between actual and predicted. So this is what I am talking about. This is the deviation, or this is the leftover. And in this column, we are taking the square of these residuals. Okay, square of these residuals. Okay, now from this value, we can, or for this outcome, we can see that for some combination of this two-dimensional data, we can get the minimum residual sum of square. So that will be considered as the minimum error, and with that consideration, we can get the best fit line. So if we plot this data on the xy plane, and then we try to find out, or then we try to determine the best fit line, then obviously some best fit line will be get, for which we will get a minimum error. The sum of residuals, as I said, that sum of residuals equal to 0. Why sum of residuals will be equal to 0? If we take the if we represent this data, let's say we are representing this sum of residuals in the range 0 and 1. Okay, then what will be the sum of residuals? If we get the sum of residuals, let's say there is no leftover. Each and every data points are lying on the linear regression line or regression line. Then we could say that the residuals will become 0. Okay. Now here the base fitting line minimizes the sum of square residual. As I said that when we get the base fitting line to the data points in the xy plane, then we could minimize the sum of square residuals. An interpretation of slope when we see the slope, then the expected change that we see in y for 1 unit increase in x. Okay, similarly for when we say the expected value of y when x is found to be 0. So as I said that when we when we found that x is 0, then we will get the expected value as intercept. Okay, now the question is, since we are determining the best fit line to these data points in the xy plane, now how we will consider this model parameters. So here the model parameters are slope and intercept. Okay, that we have to determine from the given data set. Now how we could do that, or how we could determine the model parameters m and c. So here there is a correlation. So we are trying to find the correlation. This is the m. This is actually m. Okay. So m equals to this correlation. We will use this correlation equation for getting the m value. Okay. And we will use this m value. We will use this m value in two different equation. Okay. That means two different way we can get the intercept. So this is actually the intercept c. Okay. So c equals to this summation over yi minus m into summation over xi, which is divided by n. Okay. So this is one form to get the intercept value, and we can use the other form also, where c equals to, so here c is given by r multiplied by standard deviation of y values divided by standard deviation of x values. Okay. And this is the equation to get the standard deviation. Okay. So we can get the standard deviation for y value. So y value means that if we consider the CGPA problem, then here y value becomes the CGPA and x value becomes the ER. Okay. So from that data set, we will easily get the standard deviation of y values, standard deviation of x values. Here from this correlation equation, we are getting this slope. Okay. And when we put this slope into this equation or into this formulation, so two different way we can compute the intercept value. Okay. Now we have determined slope and intercept, these two model parameters value from these formulations. And uh, for the coming years, or if we consider this equation mx plus c, so c is determined, m is determined. Okay. X is given, that is CGPA is given. Now we have to, no, okay, ER is given. Now we have to determine the CGPA or dependent variable or outcome. Okay. So this X is known as the, so see different three different way you can call this variable. So this may be explanatory variable, or we can say predictor variable, or independent variable. Now if such problems are given to us, then this is very easy for us to compute the predicted value or the outcome. Okay. Now if we are having more than one independent variable, suppose this is mx1, then we are having m1x1, m2x2. Okay. M2x2. Now in the last class we have talked about the population density estimation problem, where we saw that there are three different columns, one for year, another for, that means three different attributes, one for year, another for population growth, another for growth rate. Okay. Now in a particular year or the coming year, if we try to predict the growth rate, then we can consider this population growth and the year population growth and year as the as independent variable. Okay. So there will be there will be two variables, x1 and x2, and we have to determine the growth rate. Okay. In the coming years. So for this type of problem, we can get multilinear regression model, and in multilinear regression model, we will have more than one independent variable or more than one explanatory variables. Okay. If you have any questions, you can ask me. Otherwise, we will stop now. In the next class, we will start logistic regression. If you have any questions, you can ask me. Otherwise, we will stop now. Okay, that's all for today.